Welcome to my first session of the talks. I want to thank the organizers, Denise and André, for putting this conference together. It's very great to see so many women in quantum in one place. Today I'm going to talk a little bit about trapped ion quantum computer and for how we went from research to marketplace. My name is Patty Lee. I'm the chief scientist at Honeywell Quantum Solutions. And I'll also talk about my personal journey, which is also part of the trapped ion quantum computer evolution. Here we have pictures of our hardware, from cryo to vacuum to some electronics. And we use our lasers to manipulate our ions to do quantum operations. And in the middle here is our actual trap that we use in our commercial system. And that is a key enabler for what we do. Let's see. So Honeywell has decades of experience in different technology areas that are quite relevant to trapped ion quantum computing hardware. You can see here. But the technology itself is not enough. We have also need people to make this happen. So we have a team of more than 100 technologists to make scientists and engineers in the field of atomic molecular optical physics, theoretical physicists, quantum information, and also in many engineering areas like electrical, mechanical, optical, and software, and etc. I'm going to hold on. I'm going to pause and make sure this is. So, okay, I think this is working. My role as a chief scientist here is to coordinate all the efforts of this team of 100 plus people and make sure that our efforts come together to build the best quantum computers we can and make it accessible to people to use. We also are developing technology that are necessary so we can continue to scale up and improve our systems for future generations of quantum computing. We have a lot of subject matter experts on our team, and we want to make sure everyone put forth their ideas and pick the best approach based on science. So certainly I provide technical input like everybody else on the team, but we let the data and science drive the technical decisions. And in order to go fast, to compete in this quantum community, we want to develop we try to develop different parts of the hardware in parallel by having many development systems, development test beds, so we can prototype and try out different ways to do things, so we can rapidly iterate on our designs. And as soon as we have a good design, we can integrate into our commercial systems when that's ready. So we recently released our very first commercial system. It's called Model H0, and it's based on trapped ion qubits. It uses a quantum CCD architecture, has 6 qubits, has a quantum volume of 64, which is a world record. It's twice as large as the next highest quantum volume machine. We have high fidelity gates and long coherence times. And our system also has special capabilities like all-to-all connectivity. We can make high resolution single qubit gates. And we can have this very unique way of function feature called mid-circuit measurement, where we can stop in the middle of a computation to measure one of the qubits and depending on the result, change the logic operation we apply to the other qubits. We're very proud of our this system, but this didn't happen by accident. This took years of planning and execution. And before that, even before Honeywell started planning and building the system, many of the scientists on our team have been working on the fundamental research behind this technology. And so I'm going to show some of the performance benchmark we were able to do on this machine. This quantum volume benchmark was actually a scheme that was proposed by IBM because back a few years back, they realized that number of qubits wasn't adequate to tell the story of how good your quantum computer is doing. And so most of the time, our quantum computers are really limited by the errors on the system. And so in this quantum volume benchmark, the system has to be able to perform quantum programs with depth that are equal to the number of effective qubits with some reasonable probability of getting to the right answer. And so it's a very stringent test. And we ran the quantum volume algorithm from the Qiskit from IBM. And we show here in this plot that with 6 qubits, we were able to execute programs with depth 6 and be able to pass the test with very little trouble there. And in fact, our error rates are good enough that we can probably increase a few more qubits in the future at that same error rate and be able to expand our quantum volume. And so the key enabler to our system being able to perform such high fidelity operations and get such high performance is this quantum CCD architecture. It has dedicated zones. So here's a schematic of our ion trap. You can see the ions sort of live on this rail, and different zones are color-coded. Those little boxes are trapped electrodes. And so in these dedicated zones, we can perform gate operations. We can keep the ions in very short chains, so we can perform high-fidelity quantum gates on them. And the ions are transported from zone to zone, and our compiler will handle all of that automatically once it sends us the quantum program. And so it's not a new idea. In fact, this idea has been around since the late 90s. And here's a paper from 2002. It was one of the first demonstrations of transporting ions in a trap. And this work was actually done by by Mary Rowe, who's one of our scientists on our team. And so we've made a lot of improvements over the years. And so now we can do these transports a lot better and allow us to get a much better performance on our machine. So next I'll show you an algorithm that was demonstrated on our Model H0 by one of our customers. And it's the Grover search algorithm, which gets you quadratic speed up compared to classical search algorithm. And so just a little bit of historical perspective here. The first demonstration of Grover's algorithm on trapped ions was in 2005. And this was done by my good friend, Kathy M. Brickman Soderberg, and myself, among others. And back then, we only had 2 qubits. And we, in each one of these set of data, we marked one of the qubit states and then we perform Grover's search algorithm on it to to see if we can find it. As you can see, we found the mark state correctly, and so that was very nice for 2005. But now this paper that was just published by a group at J.P. Morgan Chase show them running the Grover's algorithm on our H0 machine on 4 qubits, and you can see that the data is a lot cleaner, and there are a lot more states you can search. And as they show the simulation of a couple different methods that they employed, and then the actual measurement from the model H0. And so the mark state here is very clearly above the rest of the other states, and so this Grover search algorithm really works on our machine as predicted. So this is where we are today, and this is we're very glad to be able to offer this capability to our customers, so that other people get to play around with our quantum computers. So now I will move on to tell you a little bit about how I got into quantum computing, and how we got here. We got here personally, which is a little bit intertwined with the history of trapped ion quantum computer. So when I was preparing for this talk, Denise said told me she wanted to know who I wanted to be when I grow up, and I have to say I didn't think a physicist was possible. I always loved math and science, and I didn't think I would. But when I started as a freshman at Caltech, I didn't think my background, my public school education in science was enough to get me through the physics major program there, which is very rigorous. But a bunch of friends convinced me to try it out, and I did, and I actually enjoyed it very much. But at the time, even though there are lots of professors there doing some amazing work in quantum, I was actually involved in nuclear physics, working at accelerators and figuring out how to smash electrons into protons, and also doing some work for building this anti-neutrino detector for CamLand. And so I really enjoyed it, but as I was started grad school at University of Michigan, I decided, well, maybe I want something a little simpler rather than these large accelerator physics. I prefer something tabletop. It's a lot easy. It should be a lot simpler to manage, a lot easier to run. And so atomic physics seems like a good idea. And somebody said, somebody recommended that I talk to this new professor at Michigan named Chris Monroe. And some of you may know Chris Monroe is also the co-founder of IonQ, which is also making trapped ion quantum computer hardware. And so this is a picture of my very first ion trap. There's literally, we just punched some holes in a couple pieces of metal and put it in the vacuum can, connected up. And here's a picture of those 2 ions. These are cadmium ions from my PhD work. And at the time, there were a lot of theorists that were proposing different robust gate schemes and for ion trap. And so the experimentalists were trying to implement them and to prove out that they work. And one particular scheme really stood out, which was this one that was proposed by Mulmer and Sorensen. And it seemed really promising as a robust gate, but people were struggling with keeping the qubits in phase while the system, while the gate operation is applied. And so me as a graduate student was just trying to figure this out. And it took a few years to understand that really all these different gate schemes are based on the same concept of applying a spin-dependent force to entangle the qubits. And they look very different on what it does to the qubits, but it's only because they're applying the spin-dependent force on different qubit bases. And if you just convert your bases from your typical 0 and 1 to some X or Y bases, then really the physics is all the same. And so that led to some understanding of how this phase sensitivity of this gate based on the geometry of your laser, whether you have beams coming in certain directions or not. And so we're able to show that in one configuration, you're sensitive to the optical phase of your laser. Another configuration, you can remove that phase. And that allows us to do this quantum computation and maintain that qubit phase for a long time. Before this was done, people were starting to give up on this Mulmer-Sorensen gate, and now this gate is still being used in our Honeywell H0 system, as well as by IonQ and lots of other trapped ion research groups. And so, we've made some advances. This phase-based walk got a little fancier. Rather than perfect circles, we have ellipses, rectangles, even heart-shaped things or multiple circles. But the physics is all the same. And so I got my PhD doing trapped ion work. But I didn't go straight from academic research into building commercial systems. Back then, there was D-Wave, and maybe some other companies are starting to do that. But really, there wasn't any trapped ion quantum computing in the commercial space. So I decided that I want to go and work with neutral atoms. Because I learned about these new novel phase called Bose-Einstein condensate. They're the coldest thing in the universe at a few nanokelvins above absolute zero, and I thought that would be awesome. And this group at NIST Gaithersburg happens to be working on quantum computing with neutral atoms. So I joined group as a postdoc. And while I was there, we did the first demonstration of entangling gates in neutral atoms in the optical lattice. So we have this double well lattice, and you can see here, where we can have atoms in left and right well. And we can address these individual atoms on the sides and do single qubit rotation arbitrarily on each one of those. And then we can bring them together by deforming this double well lattice, and their interaction creates entanglement. And it actually pretty neatly maps onto what's called a square root of swap gate, where these atoms, atomic qubits, can swap back and forth between the two different states. And if you stop in the middle, that square root of swap is entangling. So here's the data that shows that we have that entanglement. And then here's the data that shows how we can map out our qubits in the atoms with these pretty pictures. One of the postdoc on this experiment, Jenny Strabley, is also working at Honeywell in Honeywell Aerospace. And I'm very fortunate to get to do this with the group. And then after my postdoc, I continued with working with cold atom research. And so I got a position at Army Research Lab. And And we had we looked at different cold atom applications in quantum sensing and quantum communications. So here are a couple articles I pulled from the website talking about the research work we did. And here's a picture of my lab, our lab and our group. And at the time, we had fiber going from our lab, running a few miles down the road to University of Maryland, and we were passing entangled photons from the two sites, between the two sites. And my colleague here, Kutsia Qureshi, is now still leading that group, and she's recently entangled a barium ion with a photon and was able to convert that photon into telecom wavelengths, and so that it can be sent down the fiber. So that was very exciting, a lot of fun. What I learned from this experience working at NIST and at Army Research Lab is, it's different than the academic environment. And so each place has different missions. They have their objectives. Even though I was doing fundamental research, it's really important that the work we do is really aligned to the organization's mission. And so while I was playing with neutral atoms, the field of quantum computing kind of continued to move on, and companies started investing in quantum computing. And so we have news stories like this one on the left that says from that time, this one is announcing that Lockheed Martin is partnering with University of Maryland to form a quantum engineering center. And around that time, Honeywell also started microfabricating ion traps in collaboration with Georgia Tech Research Institute. And people were talking about building quantum computers like D-Wave does, but just with different technologies like trapped ions and superconducting qubits. And so I was aware of all those things going on, but I really wasn't actively thinking about switching career until a friend called and asked, "Hey, how would you like to work in industry for a while?" And so when I said, "Well, I haven't thought about it, but please tell me more." And one thing led to another. And so I ended up working at Lockheed Martin for a few years before finally ending up at Honeywell. People have asked me why I work for Honeywell, and the answer is simple. It's really about the people. I really enjoy working with the people on the team. They're very smart and very knowledgeable, very talented, and also motivated. But the most important thing is that they put teamwork first. And that's really key. We get enormous support from the leadership and on down. And I really appreciate everything that the company and everybody on the team has done to make this possible. And here are some of the women on our team, not all of them, because I didn't get everybody's picture on here. But I want to point out a couple of people, Joan Dreiling and Caroline Figgett, who are on the H0 integration team. And they really drive to make this commercial system possible for our customers. And I also want to thank the optics team for making the lasers and optics work. It's a lot of effort to put it all together and keep it running well. And they did a fantastic job. I also want to point out a few of the people on the executive leadership team who handles legal and finance and HR and other functions that supports our operation that makes it possible for things for our commercial system. And so finally, I'm very excited about our quantum computer, and we will be continuing to improve the performance on our system. If you're interested in using our quantum computers, please come talk to us. And it's an honor to be here, and thank you all for coming, and I hope you enjoy the rest of the conference. I'm going to go back to the screen and hope. All right. So that's my prepared presentations. I'm happy to answer any questions if people have them. I'm going to stop my screen share because that's a little too crazy there. Oh, here we go. Let's see if this works. Denise has requested the mic. Did that work? All right, I don't hear Denise. Oh, here we go. Requesting the mic. Yes. How do I give it the mic to her? Accept. Here we go. All right, let's try that. Hi, Denise.
Hi, thank you for a great talk. I really appreciate it. I just posted on LinkedIn all the women in Honeywell. So wanted to ask you, it sounds like you have a really diverse team there.
Yes. Yeah, I mean, like this is one place, probably the highest concentration of, women with PhD in optics, physics, and also also technical fields like engineering and IT and everything. Yeah, I think it's very rare to be working in a place with so many women around, in a very technical field, and so we're very glad to see that.
That's great. That's great.
And we certainly would like to have more women to join our team.
Okay. And I also have women you mentioned in HR and legal and non-scientific roles. So there's roles for the dummies like me that are biologists. I think there's many roles available at a company like Honeywell for women.
Absolutely, yeah. I think there are lots of things that have to get done. We don't want the scientists to be handling HR and all that stuff either. And so we really need everybody on the team to perform their work. And so there are definitely a lot of roles to play here.
Good. I think that's one of the messages I have for people is that there's a lot of roles for a lot of different skill sets. And I think it's important that everybody feels that there's something that they can do to contribute to this field.
Mm-hmm. Absolutely.